This is a PyTorch quantization-aware training example. I found this from this website. It's a very nice website. I strongly recommend you just go over this website because it gives very useful information. Not something that we haven't covered in our lectures, but it will be a nice preview, and it talks about this library of Brevitas. Brevitas is a library designed for Python language. Actually, in this, let me get to the slide. In this directives part of the Python language, you see a library being imported, loaded, included. It's called brevitas.nn. So, well, instead of brevitas.nn, it uses this word QNN. And in this QNN library, we have this called quant convolutional 2D layer. It is similar to MATLAB, as you can see. In MATLAB, we have concatenated different layers to create a layer graph. And in Python, in PyTorch, you do it the same way. But the PyTorch language already has these quantized versions. And if you construct your layer graph using these quantized versions, and if you use the quantized aware training capability when training your model, it will be quantized aware training, guys. It's very simple. So in a ready framework like PyTorch, it's very easy to do it. It's not different than training your network in the conventional manner where you do no quantization. You just use quantization capable layers already defined and designed in PyTorch language. So quantization aware ReLU, quantization aware linear is quantization aware fully connected layer, guys. So you just add up these layers and you construct a quantization aware layer graph. This is the first step you do when you do it in code. So guys, actually this network is trying to create the LearnNet architecture. LearnNet is one of the very first convolutional neural networks. It is constructed by Jan LeCun. If you go to the website, there are several versions of LearnNet. Actually, LearnNet is a very simple convolutional neural network, and it has a very simple architecture. Because LearnNet is a very famous guy. I mean, he's the head of the AI research at Facebook, and he was a student of Geoffrey Hinton. Geoffrey Hinton is the godfather of deep learning. He's very old, and he's from Canada, Montreal University, and actually one of his students, Jan LeCun is one of the students of Geoffrey Hinton, and also Alex Krizhevsky, the founder of AlexNet, is also a student of Geoffrey Hinton's. But LearnNet is a structure which was proposed before AlexNet. When it was originally proposed, it didn't use ReLU. Then Alex Krizhevsky found ReLU in AlexNet, and Jan LeCun implemented the idea of ReLU to its LearnNet architecture. So LearnNet architecture, that's why, have evolved in time, and it has many versions, but still LearnNet is being considered as one of the very simple convolutional neural network architecture. So if you're doing a simple test like quantizing a layer, well, you use this architecture. It's a good idea to use a simple network like LearnNet. So this is the rest of the code. You add these layers, and in the end, you have a forward function. The forward function is, so it creates a class called LearnNet, quantized LearnNet. Quantized LearnNet is a big object in which you have the layer structure and the forward run for all layers, guys. You calculate the outputs and feed it to the next input, feed it to the next input. So that's how you construct it. And it's a quantized version of it. It's very nice. You can create it if you have the quantized version of these layer blocks. But if you don't, how can you create your own? Well, you can. It's very simple. Well, models are trained using very tiny gradient updates, guys. So in these updates actually, and in the pseudocode, in the pseudocode, these updates, and as shown here, these updates are very tiny bits. If you quantize them, you lose a lot. So actually, it's not a good idea to quantize them because we do need high precision there. So how to do it? So what makes sense is to quantize some part of it and not to quantize some part of it. Because in the end, what we need is quantized inference. We need the weights to be quantized. We need the actuations to be quantized. And we don't want any accuracy loss. So we are going to do something called fake quantization, guys. We're not going to totally quantize everything. We are going to quantize only a part of the network. So how are we going to do it? We're going to create something called the fake quantization nodes. Actually, this was how it was implemented originally in TensorFlow. And actually, you can implement this like this in MATLAB by creating your own layers. So fake quantization nodes. With the fake quantization node, the rounding effect of the quantization is simulated in the forward pass. Okay, you are going to implement this for the forward pass. What about the backward pass? Well, actually, we don't want to change the gradient update. So the backpropagation will still work as usual, but at each iteration, when we calculate weights, we're going to quantize them. Calculate weights, quantize them. Calculate weights, quantize them. So it will be a fake quantization because we don't totally quantize everything, but we'll be just like fine-tuning the weights at each step by quantizing them and telling the optimization procedure, please don't make that step. Use these weights when you're making that step, that update. So how does it work? Actually, there is a very nice paper for it, guys. The Benoit et al. Just go to the website and read this paper, guys. It's a very nice paper. It is one of the actually I've referred to this paper in the previous slides. It is one of the first studies that talk about quantization of your training and how to do it, and it just implements a very basic idea. The idea is, okay, you have weights and biases, you do convolution, and after the accumulation, you apply a ReLU layer. That's the conventional stuff. So how to do it in training? Well, you have weights, quantize your weights, and you do your calculations. Don't do any quantization during your calculations within the training. Don't change anything. So there's no quantization node here. Then just feed it to ReLU, still no quantization at this point, and you quantize your actuations at this point. So what this guy is trying to tell us is, in training, you don't have to quantize everything. You quantize some crucial steps. You add some quantization nodes to some crucial steps to here and here. And that will be enough. You will obtain a quantized version of the network. You will do complete quantized inference. And you will lose your accuracy not much. So latency and accuracy versus graph, they provide in their paper. And read this paper. It's a very nice paper. So it is how they do it. And they call it fake quantization nodes. And it's being implemented in TensorFlow with this idea. It's a very simple idea. Actually, you can quantize them. So actually, adding these quantizations to the activation layer, actually, it is what we've said in our pseudocode. Quantization, quantizing the forward pass, quantization of the weights, and quantization of the activations. Doing nothing with the update part. That's fake quantization. That's the pseudocode of what these guys were doing. Okay, let's continue. How are we going to do it in our own presentation? How are we going to do it in our own custom layers? Imagine we are going to do it on MATLAB. How are we going to do it? Let's discuss it a bit more.